So in this video tutorial, we're going to look at an alternative way of looking at gravitational potential energy. And this is a concept that will carry forward into electrical energy and other forms of energy. And it's something called potential. Okay? And potential is like potential energy, but it doesn't have the word energy in it because it stands for something different. And the symbol for potential is a capital V. And electricity, it's another word for that, is called voltage. Something we're all familiar with in terms of the name, but not really sure what it means. So electric or gravitational potential is related to potential energy, but it's a more convenient way of expressing how deep you are in a well without needing to know the mass that's in that well. So I'm just going to give you a definition, okay? Gravitational potential energy, Vg, or define it as energy per unit mass. Okay, and the equation is fairly simple. V, that's potential, is equal to potential energy divided by the mass that's in the well. Okay, so it takes out any influence from the mass. We talked about gravitational field intensity back when we were doing gravity, and it's the same idea, where gravitational field intensity was force per unit mass. This is energy per unit mass. And if we take our gravitational equation for gravitational potential energy, we can say that's G, negative G, M all over R, divided by the little m, and we can see that the mass of the thing in the well goes away, it cancels out. That's the whole point of this. So we're left with a negative G, M all over R. And that says, no matter, what it basically tells you is, if you want to know the gravitational potential, it's simply based on where you are relative to whatever planet in question is. What it does not take into account is the mass of the object in the well. If I want to turn it around, what we can say, and I don't have an equation there, is we can say then, if you know the gravitational potential, you can say the gravitational potential energy is simply whatever potential you're at times the mass that you put at that spot. So this can be a really useful way of finding gravitational potential energy if you're given this. Okay, so let's calculate Vg and Ug near the surface of the Earth. Now, we've actually already done Ug. Ug we did earlier in class, so I'm not going to repeat that. But let's calculate Vg. Vg, by definition, is Ug divided by m, where m in this case is the 1 kilogram object. Well, we calculated the Ug earlier to be about negative 6.67 times 10 to the 9th joules. If we divide that by 1 kilogram, we get the same number, negative 6.67 times 10 to the 9th, but it would be joules per kilogram. Which means that when you're at the surface of the Earth, for every kilogram that you put at the surface of the Earth, you're going to have a potential energy of negative 6.67 times 10 to the 9th. So if you bring in 100 kilograms, you're going to have 100 times more potential energy. That's pretty much it. So problem number 1 from the homework asks you to calculate gravitational potential, and it would be basically using this equation.